All right, I just want to try one like this. So we did one at the very end really fast last time, but I wanted to give it a few more moments because there will be one on the homework like this. So we're going to do the partial fractions. The problem with just directly doing the partial fractions here, remember the partial fractions is this thing where you go like you factor the bottom, which in this case is a -2 and a -3. So you do something like this. And then this A and the B, they allow you to express this as a fraction. But remember, the method for doing this involves you set this equal to some stuff, and there are two variables here. The way you're able to actually solve for two variables is you make two equations based on the coefficient on x and also the coefficient on the constant. But the problem here is the top is a quadratic, which means you don't just have two coefficients. There are actually three coefficients, which doesn't match the number of variables over here, and so it just doesn't work when you try to set it all up in exactly the same way. So instead, we reduce the degree up top by doing one step of long division. So here we are going to divide, and it says 3x, sorry, I did it backwards, x squared minus 5x plus 6 is dividing into 3x squared plus, now because I'm doing long division, I'm going to insert a 0x plus 18. I hope you're all at least a little bit familiar with this polynomial long division. Here's a fun fact. Anybody know the name of this? It has a name, a historical name. This is called the vinculus. Tell your friends. The vinculus, yeah. Anyway, let's do the long division. So what you should do, you think of these various terms here as if they were the digits of a big number, and you should look at the leftmost sort of digit here and the leftmost digit here, and you divide them, which is to say you figure out what's the number which you should multiply this by to equal that. And in this case, it would be 3 to make them match up. So I put a 3 up here. So that thing outside the vinculus goes into the other thing 3 times. And now to continue the long division, here we need only one step. But we now multiply the number up here, this partial quotient, by this thing. And it becomes, and I'm going to write it right underneath, 3x squared minus 15x plus 18, right? And then we subtract as always. And the top digit, or the leftmost term, ought to cancel if you did it correctly. If it doesn't cancel, it means you messed it up. I subtract, I get 15x, and then the 18s actually go away entirely. All right? And here we stop. Once you get to a constant up here, you stop. Although actually you can continue, but in this setting, it's not helpful to continue. And this is now the remainder. All right.
-15.
I think it's positive. Yeah, it's a little ambiguous because I wrote that minus right there, but I am subtracting everything here. Yeah. Maybe it's better if you don't write the minus sign. All right, that's the remainder. Now, if you were a little kid, you would say something like 3r15x, but we don't say that. What that means is the answer is 3 plus an extra bit of 15x over this stuff. So what that is, having done the long division, that whole integral translates to what the numerator was. Well, I don't care what the numerator was anymore. It is now 3 plus 15x over x squared minus 5x plus 6, like that. All right, and now that the fraction part, I'm just going to leave the 3 there for now, and I'm going to do the partial fractions on this part. Partial fracs. All right, and now it's going to work with that sort of the big A and the big B. So I say 15x over this stuff equals A over, I might as well do it the same order. I put A over x minus 2 plus B over x minus 3, like that. And then I hope you recall the partial fractions technique. So on the right-hand side, I'm going to make a common denominator and actually add this up. The common denominator is the same stuff on the left. It's the product of those two things. And on top, I have a times x minus 3 plus b times x minus 2. Up top, that all, if I distribute, is ax minus 3a plus bx minus 2b. And I'm going to group them in terms of x's and constants. It says a plus b x minus 3a minus 2b. And all of that equals 15x. I'll write it as 15x plus 0. The constant part is 0. The x part is 15x. And now we can equate the like coefficients. So I go 15 equals a plus b, and also 0 equals 3a minus 2b. And then we need to solve the system. This can be a pain sometimes, but I'm going to try and give you ones where the system works out nicely. So I'm going to say b is a minus, or 15 minus a, just to solve that one for b, and then plug that into the other one. 0 equals 3a minus 2 times 15 minus a. That says 3a minus 30 plus 2a. That's 5a on the right.
Did
that mess it up?
Negative?
Negative 3a. Yeah, thank you. All right, I did mess it up. Negative 3a, negative 3a, negative 3a. Glad that guy left, huh? He would have been really mad. Yeah, I think I now am going to agree with what it says on my paper. So I can add the a's to the other side. It'll be just a equals minus 30, right? Okay, and what about b then? B is 15 minus a. So this would be 15 minus negative 30. That's 45. It's enormous numbers. All right. Anyway, all of this means, having done the partial fractions, our original integral now, in these types of problems, the integral is typically easy to do. It's just getting there. It's going to be a, which is negative 30 over x minus 2, and then b is 45 over x minus 3, like that. This is, the hard part is over now. Now we just have to do this integral. Anybody remember how these goes? What do you get from the 3? That's the very easy part. 3x, yeah. How about the next one? 3x. Yeah?
Negative 30 ln x minus 2.
Right. Each of those denominators just becomes ln of something or other. And the numerator just stays as a constant multiple. And then 45 ln x minus 3. Let's see. All right. And I think that'll do it. Thank you for your attention. And I hope you all have a nice little break.